Okay, so in this talk, we're going to look at what problem descriptors solve, how descriptors are implemented, and how you use them. And yeah, show me something cool that uses descriptors. So I'm going to show you something that I think is cool. Hopefully you think it's cool too. A bit of assumed knowledge. So if you know Python classes and you're familiar with decorator syntax, you'll be fine. It will also help if you are familiar with getAttr and setAttr and friends. So the motivation of descriptors. The first point I'd like to make is that attribute access is an abstraction. In Python, there's a default implementation that is to read and write values in an instance dictionary. But that doesn't have to be the implementation of attribute access. And there are reasons, the default implementation is well understood. It's often appropriate. But it is also useful to be able to augment or indeed replace the default behavior of attribute access. So some use cases might be ORMs or other data abstractions, type checking or other kinds of validation, callbacks, so for extensibility or for audit trail, you might have other use cases. Yeah, things I haven't thought of. So what about getAttr and setAttr? Can you use these mechanisms to do this sort of thing? Well, yes you can, but there are some limitations. So you can only have one getAttr per class, and likewise for setAttr, delAttr. So if you want different behaviours for attribute access in a single class, you have to multiplex them all into the one method. And you cannot easily share and reuse these implementations, except through inheritance. So we want custom attribute access behaviours. We want those attribute access behaviours to be easily reusable. It would be nice if we could have a declarative way to use these non-default attribute access behaviours. And it would also be nice if we can easily parameterize those behaviours. So you can use descriptors to do this. In the standard library, there are some descriptors that you have probably used. So the first one is property. So is there anyone who hasn't used property? Hands up? Yep, no one. Everyone's familiar with it. Great. So property is actually implemented using descriptors. There's also a class method and static method. And these ones are used to, in the case of class method, instead of having the object itself as the first argument to a method, so the invocant, you can replace that with the class object. And with static method, you just throw it out, do away with the invocant argument altogether. So these are also implemented using descriptors. There's also functools.partial method and a few others. But those three at the top are certainly ones that most Python programmers are familiar with, but they might not have been aware that under the hood, they were actually using descriptors. So what's a descriptor? Well, there's a descriptor protocol, and it's these three methods. So a descriptor is a new style class that implements one or more of these methods being done to get, done to set, and done to delete. Now, in these method signatures, self is the descriptor instance. So it's an instance of a class that has these methods. The owner argument here in get is the class in which you are using descriptors. So it's not the descriptor class. And instance is an instance of owner. However, in the case of get, where the owner method appears, if you're using get to access that attribute on the class object that's using the descriptors, rather than an instance of the class, then you're not dealing with an instance. In that case, the instance is going to be none. So this is an example of a descriptor. It's called type constraint. And it is a new style class. So it subclasses object. We have a constructor method, dunder in it, and it just takes a constraint, which will be a type or a tuple of types. And in the constructor, we're just going to save the constraint, and we're going to initialize a weak key dictionary for storing the data that we're going to store in and access in these descriptors. Done to get. Now this is what actually makes it a descriptor. So the interpreter, when it's resolving attribute access, will look and see does the type of the object that we're performing the attribute access on for this attribute, is it an object that has this method? If so, it's a descriptor. So that's all a descriptor is. And there's also a set method for this one. The interesting thing that we do in this descriptor is in set, where we check whether the value that we're setting is an instance, or sorry, is not an instance of the constraint that we supplied to the constructor. In that case, we raise a type error. However, if it is an instance, then we fall through to the else, and we're going to set the value in the weak key dictionary up here. Now, the reason we used a weak key dictionary is for garbage collection reasons. Because we're storing instance data in the descriptor rather than the instance itself, we want to be able to allow that instance to fall out of scope and be garbage collected. So we use a weak key dictionary. Otherwise, we'll just hold on to that memory forever, which is probably not what you want to do. So we now have a reusable alternative implementation of attribute access. And the particular implementation we have is one that checks the type of a value when we set it. It's also parameterized over the constraint. So you can instantiate a type constraint descriptor that checks whether something is an integer, or you can check that it's a string, or any arbitrary type, because as you saw in the implementation, it just uses the isInstance facility. Okay, great. So how do we use it? This is how you use a descriptor. You assign an instance of a descriptor class to a class attribute in the class definition. So here's a class. It's just a two-dimensional point. We have attributes x and y, and each of these is an instance of type constraint. And we use for the constraint parameter numbers.real. So that will be integers, floats, but not complex numbers, and certainly not strings or other kinds of crazy things. Then we have a constructor method that just takes the x and the y and sets self.x equals x, self.y equals y. But if you construct this with a string or a complex number, you're going to get a type error when you construct it, because at this point here, the descriptor's done-to-set method is going to be invoked, and it's going to perform that type check. So this is just an example of a fairly simple descriptor and a fairly simple class using that descriptor. But you can see you have the advantage of type checking, and that type checker descriptor can be reused in any class you want, and because it's parameterized over the constraint, so the types that you're interested in constraining that attribute to, you can reuse it in all kinds of different situations too. If you have a class that you have attributes that are supposed to be strings, then you can instantiate a type constraint descriptor with an argument of string, and it'll make sure that you can only ever set a string for that attribute. Okay, so the example on the previous slide uses two type constraint descriptor instances, one for x, one for y. And they're used declaratively. So it's as though you were saying x and y is constrained to real numbers. I think you'll agree that that's fairly literate code. It's clear what that's supposed to be doing. Now we could use other kinds of descriptors alongside x and y. So this gets around the problem with getAttra, where we would have to multiplex these different behaviours into a single implementation of getAttra, or likewise with setAttra. In this case, if we have two different attributes that we want different behaviours for, we just use the appropriate descriptor for each of them. Okay, another example is class method. So is anyone not familiar with class method? I did explain it briefly before. Okay, so in this case, again we have a constructor. This one's going to take a function. Now that allows us to use it with the decorator syntax. We have a done to get, no done to set, because it doesn't make a lot of sense in this case. And in done to get, we simply take the original function and wrap it up in a new function that just takes an arbitrary number of positional and keyword arguments. And we then call the stored function with the owner, so that's the class on which this descriptor is being used, as the first argument, and then just splat out the positional and the keyword arguments and return the new function. And so that allows us to use this descriptor just like the built-in class method decorator in the standard library. So we have a foo class here, and we use the class method descriptor we just defined with the decorator syntax. And in this case, it's just an example, so we're going to say, hey, we call the class method. Okay, great. So that's just another example of a different kind of descriptor you can define and how you would use it. So implementing descriptors. They've been around since Python 2.2. They're in all of the alternative implementations. So you can almost certainly use descriptors. If it wasn't apparent, I'd just like to reiterate the point that a single descriptor instance for a given attribute is shared by all instances of that class. So with the type constraint example, it doesn't matter how many points you instantiate. There's only ever going to be one instance of descriptor for X and another instance of descriptor for Y. And that's it, just two instances of the descriptor object. And you can implement descriptors using the C API if you need to do that for some reason. So some other implementation considerations when keys collide. So if you have data in an instance dictionary keyed by the same key as something in the class dictionary, and that something is a descriptor, just stay with me, it's a little bit convoluted. What happens? Okay, so descriptors that define get and set are called data descriptors. Those that only define get are called non-data descriptors. So the class method example would be an example of a non-data descriptor. So what's the difference? The key collision for a descriptor in a class dictionary and a value in an instance dictionary. For data descriptors, the descriptor mechanism always takes precedence. So the data in the instance dictionary will be ignored in all cases. But for a non-data descriptor, the instance dictionary will take precedence. So you're probably not going to run into issues with this, but it is important to know what the interpreter is actually doing when it resolves the attribute access. So to define a read-only data descriptor, you must implement done to set, but in that case you would just raise an attribute error and say, hey, sorry, I'm read-only. You will need to define done to set. Storing values, okay. So if you're going to use descriptors as a data abstraction and you do need to store data somewhere, you need to decide where to store it. So you have two main avenues here. You could store it against the instance, so somewhere in the instance dictionary of the instance of the class using the descriptor, not the descriptor instance. Or you could store it in the descriptor object itself, and that's what we did in the weak key dictionary example we saw just before. So I prefer storing it in the instance dictionary somewhere, somehow, because I think instance data should be owned by the instance object, and it also does away with any issues around garbage collection. Once your object falls out of scope, it can go and get garbage collected, and you don't need any extra mechanisms in your descriptor to handle that scenario. However, there may be something about your use case, or there may be space or performance considerations that commend one particular approach over the other. If you're not sure, try both ways, do some empirical testing, work out what the appropriate way of storing data is going to be in your case. So I'm not telling you which way to do it. I'm just saying I prefer a particular way where it's feasible. Descriptors and metaclasses. Okay. So I've heard a few people at the conference here saying, oh, metaclasses, you know, don't use them 99% of the time. You do not need one. If you want to use a metaclass, you must know why you need it. Okay, I generally agree with that. But I also believe in knowing your tools, learning your tools. So I would encourage people to go and actually learn about metaclasses and experiment with them. Not at work necessarily, but just in your own free time, because there are use cases where they're great. So the metaclasses can look in the class dictionary when the class is defined, and if it sees particular descriptors of interest, it can go and can set up some additional state or set up some, scaffold up some network connections or whatever crazy things you want to do. And then you can have your descriptors interact with that extra context that the metaclass sets up. You can do some pretty powerful things, but make sure your use case justifies the complexity. Know why you're doing it. I'm not going to talk more about how to use metaclasses here. It's an in-depth topic for a different talk, perhaps. But I will say that this is what I did in Elk. Okay, what's Elk? Elk is an object system for Python inspired by Moose for Perl. So are there any former Perl mongers here? Any other reformed Perl mongers? One over here, okay. Okay, so Perl 5 has a fairly obtuse object system by default. But almost anyone doing object-oriented programming in Perl is going to be using a library called Moose. Moose is awesome. When I first went onto a Python project after writing Perl for a couple of years, I really, really missed Moose. Now, I did get used to Python and not having Moose, but I never stopped wondering what would Moose look like if I implemented it in Python. And then one day, you know, I had a free weekend with not much else to do, so I'm like, okay, great, I'm going to do it. So I wrote Elk. So the features include roles, method modifiers, attribute delegation, default values, lazy initialization, read-only attributes, required attributes, type constraints, and a whole lot more. And the things with the star are using descriptors somewhere in their implementation. So some of those are implemented entirely using descriptors. Others are implemented using the descriptor, you know, just for one small facet of the implementation. And you also get constructors for free, so you don't need to write a dunder init. And it works well with inheritance, and there's a comprehensive test suite. So this is an example. So again, we're going to use the two-dimensional point as an example. So class point, and we just extend elk.elk. Two attributes, x and y, and they are ElkAttributes. This is a descriptor. So we'll say they're read-write attributes. The type constraint is that they must be a real number, and they are required attributes. They cannot be omitted. And likewise for y, and just as an example of the inheritance, class point3d point, and we just add in a z attribute. Okay, so what happens when you try to use this class? Well, let's instantiate it with no arguments. Boom, traceback, attribute error. There was a required attribute and you didn't provide it. Okay, so we're going to fail early. That's a good thing. Okay, well, we'll supply x and y this time, but that does not look like a real number. And sure enough, we'll get a type error. Sorry, the y attribute must be a real number. So again, we're going to fail early if you do something unreasonable. That's a good thing. Okay, well, we'll construct the point at the origin, x and y as 0. But then we'll try and set the attribute y to be the string. No, sorry, still can't do that. Still needs to be a real number. Or if we take the attribute, take the object we constructed, so we have a point at the origin, and we want to delete the x attribute again, is going to be prevented. It's going to raise an attribute error and say, sorry, that was a required attribute. I'm not going to let you delete it. Okay, so that was just a very basic introduction to Elk and what it looks like to use Elk, some of its facilities. How is it implemented? Let's look at the descriptors and have a look at some of the things we're doing to make this behaviour possible. Okay, so this is the done to get for the ElkAttribute descriptor. First of all, I'll just mention about this decorator. So because we're working with dictionaries, but in the context of attribute access, we want to catch key errors and raise an attribute error instead. So this descriptor, this decorator just takes care of that for us. Okay, ignoring this if instance is none, return self. If the ID of this descriptor object is not in the ElkAttribute dictionary on the instance, and if it's not in the ElkLazy, and if it is in the ElkLazy dictionary in the instance, then we're going to invoke this closure here, which will construct a value for that attribute, and we're going to set that. So we're going to call self.doneToSet, which is a descriptor method, and set that value. So this section of the code here is implementing the lazy initialization feature. So if you have a attribute whose value is expensive to compute and you might not need it, you can actually defer that computation until someone's actually asking for it. Then you can incur that cost, set the attribute, and at the end, we return it. Now, as I said earlier, I personally favour storing instance data in the instance. So the convention that I use is this done to ElkAttribute attribute of the instance, which is a dictionary. But in order to have multiple ElkAttributes living harmoniously side by side in the same object, we need to make sure that their keys don't collide. So for that, we just use the ID of the descriptor instance, which is going to be unique for every descriptor instance. So that avoids us having to assign additional keys or names to our descriptors manually. We just use the fact that every object in Python has a unique ID to key the dictionary. This just returns an int. In CPython, it is the address in memory of that object, but that's an implementation detail. It's pretty much beside the point. Okay, with doneToSet, we're going to see a few more features in play here. So if the mode of self, the descriptor object, is read-only, so you saw on the slide back before, we had mode equals RW, read-write. But if it's read-only, then we're going to say, sorry, it's a read-only attribute. Going to raise an attribute error. If the type is not none, so there is a type constraint, and the value is not an instance of something that we've given in the type constraint, then we're going to raise a type error. So this is very similar to the type constraint descriptors behaviour that we implemented earlier in the talk. So yes, indeed, type error. Sorry, the attribute must be a whatever this type is. And then finally, if we make it to the end, then we're going to set that value in the ElkAttribute dictionary, keyed by the ID of the descriptor object. And in delete, again, we're going to catch key errors and turn them into attribute errors. And if it's a required attribute, then we're going to raise attribute error. Sorry, you can't delete that. It's a required attribute. Otherwise, we will delete that from the ElkAttribute dictionary. Again, the key is the ID of the descriptor object. Okay, so that's all I wanted to show you. Hopefully, I have proven to you that you can do some useful things with descriptors, and that is a useful feature of Python that you hopefully will want to learn more about, so that when you hit these use cases where getAttra and setAttra don't quite cut it. You have in your toolbox descriptors, and you can go forth and implement what you would need to do in a nice, elegant, reusable way. So what have we seen? We've seen that we want reusable alternative attribute access behaviours. And there are many use cases for those: ORMs, audit, validation, etc. That getAttra and friends don't cut it, but that descriptors can solve these problems. We've seen the descriptor protocol and some implementation examples and some examples of how to use descriptors. We've looked at a few technical trade-offs and gotchas, and hopefully with the Elk example, I've shown you that, yeah, you can do some useful and powerful things with descriptors, and especially when you combine them with metaclasses, but make sure that your use case justifies the complexity. But go learn about metaclasses. They're really cool. Resources, there's the how-to guide and the data model reference in the Python docs. That's Elk if you're interested in Elk, and that's Moose if you're interested in Moose, just to see what it was that I was actually trying to accomplish. And yeah, thanks for listening. And are there any questions? Can you go to the mic?
Is it possible to chain descriptors?
Is it possible to chain descriptors?
Say you had a type requirement and also like an input validation, and you wanted to apply them both to an attribute.
The descriptor protocol doesn't give you a way to do that, but it might be possible to use multiple inheritance of both those descriptors and combine those behaviours in a way that sees you not repeating yourself too much.
All right, cool.
Chaining of descriptors is sort of possible and is actually in some respects required. The class method example you gave is actually technically wrong. It's actually mirrored. All you're doing though is mirroring what is actually a bug in the Python library. I lodged a bug about it, but technically in that example in the where you, I don't know if you can bring the slide up quickly or not, but you in the get underscore get, you were actually then calling self.func with the class method argument as the first argument. Technically, you're supposed to actually do a underscore get on the func with the class method and then call the result if you're going to honour that descriptor protocol properly when calling that wrapped function. So I don't know quite what he meant by chaining, but to me that's what I interpret as chaining, is that you're honouring the application of the descriptor protocol on something you're wrapping. It should be applied down and done consistently, because otherwise technically you're breaking the Python object model.
Okay, right. Well, I'd like to talk to you about your specific points about the class method example. I tried it and it did work. However, my interpretation of the previous question is more about composing the behaviour of multiple descriptors into a single descriptor that exhibits both of those behaviours in that case.
In terms of if you want to try whether it works or not, it'll give you what you perceive as the desired result. But if you take your class method implementation and wrap it around another class method implementation, or bad example, just if you were to wrap it around a decorator which happened to be implemented as a descriptor, the fact that you have not done the descriptor protocol on the inner one means that it will now no longer function. So it's to do with the nesting. As I say, depends on what he calls nesting or chaining.
Yep.
Or so on.
I see what you're getting at. And yes, that was a naive example. And you know, I'd like to work on a better example with you shortly. Cheers.
Great talk. I really enjoyed it. Have you done any analysis on what sort of overhead you have with this sort of thing, like inheriting from the elk object?
With Elk specifically, I haven't. That was specifically not an objective of Elk, so performance. You know, I'd be really interested if people do want to use it or do want to profile it. I'd love to find out what the performance and the overhead is like. But for me, it was really just an exercise in the question of what would it look like if Moose existed in Python, and how can I make something that implements the features of Moose but feels Pythonic, feels like idiomatic Python. So that was my objective with Elk, but yeah, I'd be interested to know those things. Yeah.
I suppose my question follows quite well from that. Do you know anyone using Elk?
I don't know if anyone's using it. I'd love to know if they are, yeah. I don't even use it for anything. I just wrote it for fun. So. Okay, we're out of time. Thank you.